Hi everybody, we're actually here. Just a second. Oh, that's good. So what this means is that our audio latency is very low at this point. So what I'm going to do is I'm going to transition here. Hi. We were just taking a little bit of time to set up the connection for the students, Carnegie Mellon students. I also think someone here has their speaker on. If you have your speaker on, do you have headphones? So could you either mute your mic or switch to headphones? Oh, I know what happened. That's my mic. Ha! Okay, now it's much better. Okay, thanks everyone. Thanks for putting up with this. This is just so you know, we are now using actually low latency, and I think we're pretty good on latency, right? I'm gonna hold up my hand like this, and there's a 1, and I think that we're able to get very quick feedback. So this is probably going to be as good as much better than what we could get before. I'll say I chose to use the YouTube Live medium for streaming this class because, in my opinion, it seems to me that YouTube Live gives better frame rate and maybe a more clear picture than what usually we can get on a Zoom webcam. Of course, students, if you have some feedback to give about this, we'll take some feedback at the end of the class. Okay, great. So let's go ahead and get started. And I'll always be kind of looking in this direction because that lets me see if there's any feedback or anything coming from our class. So let's see, what did we have last time? So last time we were talking about under what conditions you could get that a very large complete subgraph was contained in something which had a lot of epsilon regular pairs. So I'm going to again draw a very brief picture of what we had last time. Let's call it the proposition, right? What we had last time was that we have this bunch of clusters. Let's call them V1, V2, and all the way to a VR. And over there, just a second, I see what has happened. I need to go and, one moment. So it looks like the whiteboard, the drawing board didn't connect across. Let me see why that is. Just a second. So blackboard sequence, we're here. Just a second. Good. Now it's across. Okay. Here we go. We're back in business. So we have here, now we also have a screencast of the board, so this works. And we had all of these different clusters, and each cluster had size m. So what we had here is that if each cluster has size equal to m, and we also had that all pairs are epsilon regular. We had that all pairs of clusters are epsilon regular. And we also had that all of the pairs have density at least delta. Okay, so those are our two key parameters. So once we have this situation, and in our head we're always thinking that we're probably going to use this with epsilon much less than delta, which is much less than 1. So that was the plan. And then from all of this, there was some conclusion. I want this to be more interactive since we actually have real time now. What was the conclusion? We have some more conditions, of course. There will be some more conditions I have to write, and then somehow there's a then. What was the goal of this? Feel free to raise your hand. Let's go ahead and use that method, and then we can probably make this work since we're actually near real time. What was the conclusion we wanted to get? I see Anthony. Go for it.
We can find a multipartite graph with R partitions and T vertices in partition.
Excellent. Thank you very much. So we are able to get this multipartite graph with R parts and each part having T vertices. Now, there are some conditions in between. I will say the exact details of what those conditions are. You could always work out if you needed to, like with the proof last time. There were basically two conditions. Does anyone remember anything about what these were? Of course, there's like some technical formulas, but does anyone remember what these conditions were, roughly speaking? And I know that I don't know how many people were like writing notes last time, so it might be harder. Although the funny thing is now that there's a YouTube video history, it's very easy just to go back and be like, what was there? But who wants to say? What were these conditions? Who can help me out? And it's okay if you're like sort of right. I'm just looking for like the moral. This is what's morally correct. What's the main thing we need here? Ah, Philip. I see Philip's already got something. Philip, go ahead, unmute your mic and let us know.
Basically, that delta minus epsilon is not too small.
Right. So
delta minus epsilon to
it's not too big. Oh yeah, not too small. Not too small. That's right. So the delta minus epsilon to some power, which is I think it turned out to be something like RT, is not too small. It's at least epsilon. So I think this might have been what I wrote. I think it's morally what I wrote. If people think this is what I wrote, give me a thumbs up, because I'll say that to me, all of the things I do are based on what is the main meaning behind here. But ultimately, where this number comes in is that's like how small your neighborhoods are getting. You know what I mean? If you remember the way the proof was working, we started out with these big clusters, and then we got smaller and smaller and smaller. And as you got smaller, I see, oh wow, you can thumbs up in Zoom? I didn't even know that. I thought there was only raise hand. Okay, that's cool. Okay, for anyone who's watching on the general YouTube live, I apologize. This class is actually customized for the Carnegie Mellon students who are paying attention to this class. And so sometimes we'll be doing a lot of interactions with them. This is just a courtesy if you're curious what happens in the classroom. But occasionally I learn cool stuff too about what Zoom can do. Good. And this thing was like the thing we have gets smaller and smaller and smaller. But the key is we need to make sure we're always able to use this lemma. And the lemma said that from one vertex cluster into like some piece here that's not too small, almost all of the vertices here have the right degree. So that was one of them. What was the other condition something like? There was some other condition there. If you could please raise your hand. There was 2 lines that I had written here. One is to make sure that somehow it's not too small, meaning I can always apply the epsilon regular property. And what else do I need? I'm looking for a hand raise this time, not a thumbs up. So, hand raise. Aditya, yes.
So we had epsilon times t minus 1 times
Yeah.
r less than half of delta minus epsilon to the r.
Thank you. Right. So what this was saying is that somehow as you are taking all of these pieces away, you're taking all of these chunks away. Each time as we were doing that proof before, we were deleting up to epsilon fraction of the vertices, epsilon fraction of the vertices. And I said, let's leave at least half of what's left over. And after the class, actually, Zichao brought up, you probably need a condition on M, because if M equals 1, I mean, you cannot find anything like this. And so actually that condition on M comes in here is because I was assuming that this is big enough. I mean, actually, what I really need is that when I eat up all of these things, this is how much of M I'll eat up. And I need to make sure there's still at least like t vertices left over, or at least one vertex left over. That's what happens at the very end. And my way of knowing that there was at least one left over, I was actually cheating by using this half. I was saying that, well, M is going to be big enough. If you actually wanted to write this out carefully, what would you actually write? So I mean, this thing was morally what we need, but really what we need is we need to say that if you had this delta minus epsilon to the RT, so this arrow doesn't mean implies. This arrow is like associated to this. What I really needed was that as these pieces were getting smaller and smaller, delta minus epsilon to the RT, that was a fraction. So it's like times M. That's how many vertices were in this last little cluster. And then when I take away this epsilon times t minus 1r times M, there should be at least enough room to pick that last vertex. It's like somehow it's at least 1. Does this make sense? I mean, this is really what we need. And of course, I might be off by 1 or 2 or something like that. But this is the Extremal Combinatorics class. We care about the asymptotics. But when you look at this, basically in most situations, M is big anyway. And so that's why I was lazy and I said, just put this thing here, because if you have at least half of that chunk left, delta minus epsilon to the RT was probably big enough, then you're in good shape. So I'll say in all of these proofs, if you go and trace carefully, then you can go and see exactly what you need. But this hopefully answers Zichao's question of how could you prove a result that has no M inside it? So then we're good with this. Okay. Now that we have this, let's go and use this to go and prove something interesting. So this result tells me that if I have this epsilon regular situation, then I can embed this very large complete multipartite graph. But how can you know that you're so lucky that you'd find this situation? At first, this situation seems extremely specialized. Like, who in the world would expect that you would be able to find this? First of all, they all have density, but second of all, they all have this thing which looks like a random graph. And that's where the Semuredi regularity lemma comes in. My plan is to prove the Semuredi regularity lemma either next class or the class after that, because ideally we don't split it across half a class. So we'll do this class to get to a good stopping point, and then next class we'll probably try to prove this lemma. But Semuredi regularity lemma, over here. Oh. So one thing is that my pen sometimes is a bit strangely sensitive. We'll do this. Okay? So this is the Semuredi regularity lemma. And I know it's been a long time since I actually wrote this thing down, so I'm going to state it again. It always starts by saying for every epsilon bigger than 0, there exists an m. And the important thing about the m is it's some finite number. And this is going to control the complexity of the object that I might get. So for every epsilon, there's some m, such that, now the interesting thing is the following result is true for any graph. So for any graph, there exists a partition into t parts where. So we have to put a few conditions down now. So these are t parts. I have my t parts. They're v1, v2, all the way around to vt. Okay, and there are some more blobs here. So I partitioned into t parts such that there are a few things about the parts. The first is that all of the parts are equal size. All sizes are equal. Well, that's not quite possible because you might not have a multiple of t in your vertices. So I'll say up to plus minus 1. Okay, so I have all these parts which are about equal size, and it's got an epsilon there. So we need to say that almost all of the pairs are epsilon regular. It is unfortunately not true if you enforce that all of the pairs are epsilon regular. So what you have is that all but less than or equal to, I'll write epsilon t squared pairs are epsilon regular. And that, by the way, is perhaps the most amazing fact about this result, which is that you can have almost all of these pairs epsilon regular. At first, epsilon regular, as we remember, is meaning it looks sort of like a random graph. And if it looks sort of like a random graph, how would you expect that to work? But somehow these things appear. I also just realized that I should turn my video off on the Zoom because that's probably just strange looking. So I'll turn my video off. You guys have a proper video from the YouTube live stream. So all but epsilon times t squared pairs are epsilon regular. And now there's also another important condition. Can anyone, I just want to see if people are following or remember some of this. Like, what's the other important condition? Right now, as I wrote, the statement I wrote is trivial to prove. Completely trivial to prove. Liam. Liam, you're good.
You need t to
Yes.
not be so large that the parts are tiny.
Okay, so we have one condition that t can't be too big, so I can write t less than m. But there's another condition. So yes, actually that's trivial to prove. If I'm allowed to make all the parts have size 1, that is very easy. There's another condition. Liam, your hand still looks up. What do you have?
There's another.
Oh, your hand's not up anymore. So what else do I need? Oh, I see Ariel.
I see Ariel.
T is greater than 1.
Greater than 1 is good. Okay, so that's important. Actually, first of all, t greater than 1.
Greater than 1 is good. Okay, so that's important. Actually, first of all, t.
We're going to do this. Okay. But there's something else that's greater than, not just 1. 1 over epsilon. Thank you. Thank you very much. Great. We'll do this. And I'll say I have an idea of what will help to reduce the echo. I actually ordered a Bluetooth headset so that I'll be able to not have that echo coming back from my side as well. The only problem is that the Bluetooth headset was supposed to be delivered by Amazon, and now I'm not sure how Amazon's going to deliver because the state of Pennsylvania just had everything shut down. So we live in a strange time. In any case, we need to have all of these things. We need to have all of these things. Now, when you make the statement is actually feels too good to be true, and we will have a very slick proof of that hopefully in the next lecture. But this particular statement can also be very useful when we integrate it together with what we had in the previous result. The previous result was where I'm able to find this big KTTTTT. In fact, the result I want to prove next to use this has something to do with the extremal number of an arbitrary graph as long as the chromatic number of that graph is at least 3. So just a second, let me double check. Let me look at the semi-ready regularity lemma. This looks good. This is what I need. Before I say that, because I always want to make sure I wrote all of the conditions down that I need, I want to emphasize one thing. Some people look at different resources for the semi-ready regularity lemma, and somebody pointed out after my class that this is not the only way you've seen it. Some people see it where it says all of the parts are really equal size, and then there's an extra part called V0 whose size is at most epsilon times the number of vertices. That is another statement, but it turns out that that statement is equivalent in the sense that you can use that to prove this and this to prove that, where effectively, if you just take that extra piece, you can divvy it up into all of those, and putting one vertex more in each of the parts will not actually change your epsilon regular condition. Okay, but now let's continue. Let's continue on with the statement that I want to start to prove. And the statement is called the Erdős-Stone-Simonovitz theorem. So this is Erdős, Stone, Simonovitz. And we'll use this notation of EX. So I'll say for any graph H. It's really only useful if I say with chromatic number at least 3. So chromatic number is the minimum number of colors you need, so you give every vertex a color, and you never have an edge which has the same color vertices on both sides. So every graph this has the extremal number of n, h is equal to, I'll write it asymptotically, 1 plus little o of 1 times, I'll call it 1 minus 1 over chi minus 1 times n squared over 2. Okay? The way to think about this, it's important to parse anything that you see. You'll see this written in different ways. Some people write it as, maybe I'll write an equivalent form. Some people actually also write this as 1 minus 1 over the chromatic number minus 1 plus little o of 1 times n squared over 2. By the way, while I have this written here, does anyone know why I wrote chi bigger equal to 3, given what I wrote over here? There's a reason why I wrote chi bigger equal to 3. It was actually so that I can write this equal sign with the purple part. Yes, C Ireland. Actually, what name corresponds to C Ireland? I'm not sure, but you're welcome to say something.
If the chromatic number is 2, the bound is kind of useless.
That is correct. Thank you very much. And so if the chromatic number is 2, then over here I get 1 minus 1 over 1. In fact, this becomes 0. So basically, if I use a multiplicative error of 1 plus little o of 1 times 0, that's not very good. That's called 0. So that's actually not equal to this. I mean, I actually claim that that equal sign is not true if I'm allowed to put chi equals to 2, because on the left side I have 0, and the right side I have little o of n squared over 2, in the sense that I'm trying to say those are saying different things. The statement on the right-hand side is saying that it will be, the statement on the right-hand side is actually a bit more nuanced, in that even if chi equals 2, well, what this means is that the chromatic number, it has smaller order than this n squared over 2. So, it is going to follow some function which is smaller order than the n squared over 2. And the thing over here would actually not quite be accurate to say it's just 0. The extremal number is 0. But in any case, I wrote the chi at least 3 because the interesting part is to say we can actually do this with a multiplicative error of 1 plus little o of 1. And that's exciting. Then you actually are able to nail this down. Even with the normal Tehran, the Tehran number for a complete graph, we actually also get a bound like 1 plus little o of 1, because no one wants to go through and write down what exactly is the number of edges in that strange complete multipartite graph. Okay, so we want to do this. There was a proof. The proof has 2 parts. One part is very easy. one side is the proof of, we could write it as an inequality, but I'll state it as a sentence first, and then we can figure out which inequality that is. Proof of, there exists a graph with number of edges being, the bound that we want, 1 plus little o of 1, this desired bound, 1 minus 1 over chi minus 1 times n squared over 2, and it has no h. Okay, so that's the first thing I want to write down. There exists a graph with this property. Actually, when I was learning this topic at the beginning, these kind of asymptotic things always bothered me. I was like, what do you mean? Is there a specific function I'm trying to put here? The way you should read a sentence like this is, there is a construction. It is a graph, and it has no h. And, by the way, the number of edges asymptotically matches a function like this. So, just as a review, what would that graph look like? Please raise your hand if you have a graph to suggest. I'm just scrolling the window so I can see the hands raised. I want to make a graph that has no h, and it should have a lot of edges. Thank you, Liam. What do you have?
Isn't it some sort of complete multipartite graph?
Isn't it some sort of complete multipartite graph? Yes, so it is. So we'll make a complete multipartite graph. If you want to avoid the h, what we'll do is we will just make sure that there are exactly chi minus 1 parts. So here's the graph, chi minus 1 parts. Okay, and we'll make it a complete multipartite graph. So all of these edges are here, and so on. Complete multipartite graph. And the reason it has no h is because, you see, if you look at this particular graph, this graph is chi minus 1 colorable. In fact, you can color it by making each of these blobs have all vertices of some particular color. So we'll have some color for all those, some color for all those, and it's going to be a valid coloring because I never have two of these adjacent vertices with the same color. On the other hand, if this contained h, if this contained h, then h is chi minus 1 colorable. And the reason is because I would just look at it and I would say h is a chi minus 1 colorable, h has some vertices in each of the blobs, and use the blob color, use the blob's vertex color for those vertices, and bam, you have a proper coloring of h because of the fact that h has no more edges which are entirely inside one of those sets. So that's a contradiction. You're not allowed to have h be chi minus 1 colorable. This contradicts that the chromatic number of h is chi. That's a very strange type of sentence to write, but it's just like chi was the chromatic number of h. Okay, so in that case, I can just look at how many edges are in this, and we did that before. The number of edges in this is exactly that bound. So we won't do that again this time. The other proof. The other proof is the one that is much harder. So the other proof has to say that if I have this many edges, then there will be an h. I'm first going to write the sentence down here so I can compare them both on the same screen, and then we'll move to the next screen and recopy this sentence. So there's the other statement, the other side. And for the other side, I'm actually going to write something instead of the 1 plus little o of 1. And in fact, I will use this like pinkish purple type expression instead. I'm going to write that for every c which is bigger than 0, okay, there exists a big N, such that for all of the little n's which are beyond the big N is some kind of a threshold beyond which interesting stuff happens, and the little n is how many vertices we're going to have. If I have this, I'll write every n vertex graph with at least, we'll write 1 minus 1 over chi minus 1. That's a chi, not an x. Let me write it more nicely. Chi minus 1 plus c times n squared over 2 vertices, edges, sorry. has a copy of H. I want to stare at these two first for a while, because I can also see that some people are taking notes. I will emphasize one good thing about the YouTube is that we will have an immediate recording of this available on YouTube right afterwards. This is not like a Zoom classroom recording, and so anyone who wants to look back at that can. Now, if I go and look at these two statements, at the beginning when I was learning this subject, this bothered me a little because I saw these like with 1 plus little o of 1 here. By the way, it's the same as the purple, but I saw plus little o of 1 there and I saw a plus c there. But they actually mean the same thing, because if you think about the epsilon delta version of what a limit means, little o of 1 basically means that, you know, for any epsilon bigger than 0, eventually it's less than that. And so I claim that this purple thing and this green thing are the same. But another thing I want to emphasize, though, is that this bound is not like tight up to plus minus 1. These two bounds actually have very different nature, in the sense that over here I have a construction, and this is a very specific construction with some number of edges. That number of edges happens to follow this asymptotic. And on the other side, I'm showing you that anything which follows that asymptotic eventually will have, follows in this way, will eventually have a copy of H. But those two bounds are not right next to each other. You actually have leeway in that little o of 1. So I just want to emphasize this is one of these things where we don't know the answer up to plus minus 1, like with Tehran for a complete graph. On the other hand, we have it asymptotically. We actually are getting two bounds which are close to each other. Does that make sense? I mean, basically because in this Cn version that we're getting, the C we're having here is going to give a function for this little o of 1, which decreases, let's call it, very, very slowly. We will soon see what the dependence is between C and n, and somehow C gets slow, very slow, as n gets bigger and bigger. On the other hand, if I look at the construction that I drew here, where I'm saying there's no h, you could actually work out what that error was, and that error will not have any behavior which looks anything like what we're going to get here. In fact, the error here, if I were to just guess off the top of my head, I would say the error is probably something like 1 over n, order of magnitude. Maybe some of you are quicker and you can figure it out. But the point is it's like polynomial. It will get smaller as n gets bigger at some polynomial rate. This one is not even close to polynomial. We'll see soon. Okay. So is everyone with me on the green statement? Which is that all we have to do is we have to say, all right, I'm allowed to say I've got any c, it's fixed, and just show there's a big N. If so, I'm going to copy that statement to the next screen. Okay? So now we want to claim for every c which is bigger than 0, there exists a big N such that for any little n which is bigger than big N, let's write it this way, every n vertex graph with at least, let's call it 1 minus 1 over chi minus 1 plus c times n squared over 2 edges has h. Remember, h was fixed in advance. Another thing I want to emphasize is if I ever say anything that looks fishy, please raise your hand. And if I don't call on you pretty soon, feel free to open your mic and say something. I actually still haven't figured out how to make Zoom prioritize the hands on top. Maybe after the class we'll have a discussion of any tips on Zoom. But let's finish this up. Okay, so now I need to show it has an h. So at this point, I said that we're going to use the Semiretti regularity lemma. So in that case, I think the first thing we should do is we should apply the Semiretti regularity lemma. So let's go with the proof. Proof. I still need to figure out exactly what causes the pen to sometimes do that, but let's do this. Proof. So we'll call it SRL because that will help save me from writing these long words all the time. Apply Semiretti regularity lemma with epsilon equal to something. And we don't know what it is yet. We will decide. Okay? And the way that this proof is going to work, I want to use the result I proved last time. And just to quickly flash back to the screen, what we had last time. Oh no. It looks like the screen froze. Just a second. So this actually sometimes happens. So I actually have to figure out why this is a program that I compiled myself. Okay, we'll get rid of that just a second. So that means we actually don't have a last time, but that's unfortunate. Oh no. Okay, so we will just we will just continue on as we were. Unfortunately, the previous screens are not here, but thankfully they are on the YouTube Live, and I have to figure out why this program occasionally stops working. But what we have is that, again, so I'll just summarize what we have. We're given the number of edges is going to be, let's call it equal, well, it's bigger equal, 1 minus 1 over chi minus 1 plus c times n squared over 2. And our goal is to go and find an h. I mean, that's what we're trying to do. We're trying to find h. And we apply similarity regularity lemma with epsilon. We'll decide later. And the thing that was there before was also we need some delta. So I'll also say that's not part of similarity regularity lemma, but we'll say let delta equal something as well. So we'll choose this delta, and that's going to help us to go and figure out, that there is this interesting object inside our graph. And the thing that we keep in mind is that we will use the epsilon is the smallest. Epsilon is smaller than delta, is smaller than 1. So that's what we're going to use. And we will choose these later. And we need to define what the n is at some point. So whenever you apply similarity regularity lemma, what we get is we get a bunch of parts, v1, v2, all the way up to vr. So we have all of these parts. And now the thing we had before was something that was interesting whenever you had some r parts which were all epsilon regular to each other. And so when I look at this picture, this tells me that it's most interesting if I can try to focus on the parts which are epsilon regular. And so the way that all of these proofs of regularity lemma, using regularity lemma work, is you then, after letting these happen, we do a few steps. We delete all of the edges in each of the VIs. So each of the VIs has some size. We delete all of the edges inside it. The next thing you do is you delete all of the edges between VIs which are not epsilon regular. Delete all edges between VI, Vj pairs which are not epsilon regular. Okay? And that will help me get rid of, and in some sense, if there's some edges between things that aren't epsilon regular, those are just annoying. Those are just causes for possible mistakes, in the sense that I don't actually know anything about the behavior between those two parts. And the third one is to delete all of the edges between pairs whose density is too low. Delete all edges between VIs and VJs of density less than delta. That's where this delta is going to come in. Importantly, delta is not a fundamental part of the regularity lemma. It's just useful for us to use in proving things. After I've done all of this, the goal will be to show that, we still have something interesting that we can use the previous result to do. In order to know that, I need to know how many edges I might have lost. So now we do some calculations, some bookkeeping. If you delete, let's use this pink, it's sort of like red for delete. If you delete all of the edges inside each VI, how do I control how many edges I might have deleted? We did a calculation like this before the break, but I want to have some people, have some participation. So if you see a way to upper bound how many edges we might delete, please raise your hand. What do we have here? How many edges? I want an upper bound on how many edges. Yes, I see Anthony.
So it's not written here, but the size of each cluster is m, right?
Oh, yes, you're right. So the size of each cluster is m. Thank you for asking. So we'll put that down over here. So each cluster size is equal to m. Okay, and they're all, let's just pretend, even if it's m and m plus 1, let's call them all m. And this m happens to be exactly equal to, then, I'll write n over t. Remember, there are t parts and there are n vertices. Okay, then continue. So all edges inside each one, what would you do?
So we would do m choose 2 to get all the edges in a single cluster.
Yes.
And we would multiply that times r for the number of clusters.
Good, thank you. So Thank you. So it's like how many edges might you lose inside one of the clusters? Oops. Sorry, dropped my pen. I got too excited. How many edges you drop inside each of the clusters times how many there might be. And that's t. Okay, that's reasonable. And now we need to control that. I'm doing upper bounds. M choose 2 is at most m squared over 2 times a t. Okay? And now I need to continue to, I guess I'll do an equality because I have an m. I'm saying m is n over t. Again, off by plus minus 1 in the grand scheme of things is not going to matter because my n is going to be huge. So this is going to be n squared over 2t squared times t, which is n over 2. Oh, and there's a t in the bottom. Okay. Can I continue to control this? I want to show this is not that big. So I see, Faye, what do you want to control this by?
I was just wondering, should the T be an R?
Should the t be an r? Yes, it should. Oh, no. So what actually happened? Thank you, guys. That's why somebody said r and somebody said t. You see, interesting. I actually want to make the r a t, if you don't mind. And the reason I want to make the r a t is because the sum-ready regularity lemma, I wanted to use with the letter t to say there are t parts. And the r is going to be something we're going to find inside it. We're going to use the thing we had before of like a complete r-partite graph. Although there we also had a t, but that t is, we're not going to use that t. So in that case, thank you. Liam, I also see you have a question. Or maybe an answer.
Yeah, that should be an n squared on top, right?
Oh, that's great. Yes, that should be an n squared on top, and we'll need that. Thank you very much. Other people. Anthony, you still have a hand?
Sorry about that. I forgot.
Oh, no problem, no problem. And I see Jung Hwan has a thumbs up, so that's cool. Okay, but anyway, if we keep going, I want to do an upper bound, so I need to keep going because t is not okay. Eventually, if I look at what I have, all I get to play with is an epsilon, and the epsilon will be set based on the value of c. And this thing has a t in it, so I'm not happy yet. I need to keep going. What else can I put here? Philip.
We know that t is at least 1 over epsilon.
Good.
So 1 over t is at most epsilon.
So that's useful. This is actually the place where we just used that t is at least 1 over epsilon. And maybe I wrote bigger equal, maybe I wrote bigger. Those don't matter too much. Here I can now put that in, and I get epsilon over 2 n squared. Okay, so now I've got that piece. This makes me happy because the amount that I lose in step 1 is something that depends only on this epsilon. I have power to decide whatever I want this epsilon to be. So if I only had to delete the step 1 stuff, I would only lose up to a fraction of this c. Basically, I'm saying if I didn't have steps 2 and 3, I could, for example, just say, you know, I want to make epsilon equal to c. And if I made epsilon equal to c, if I subtract from this much, oh no, I couldn't. I would have to do c over 2 because there's an over 2 here and over 2 there. But I could say that I've lost only a fraction of my c, and I still have some c to play with. But let's keep going. What's here? So the number of edges that I might lose in the second stage, I guess I'll use a different color. Let's put it here since my head's in the way. So how can I control how many edges are there between pairs that are not epsilon regular? Please feel free to raise your hand. I always go over here to move the computer around because I need to scroll to see if there are hands raised. But what would I do here? I need an upper bound. Yes, Bryce.
Well, we know there's at least, or at most, epsilon t squared.
At most epsilon t squared. Yep, who are not epsilon regular. And for each one of them, the most number of edges I might lose is m squared, because each part was size m. And now let's continue to bound that. Actually here, m times t, oh, that's very convenient. I didn't even need to leave this much space. I'm going to write equals epsilon n squared, because the m times t is actually the n. So we're in good shape here. This is also good because this epsilon n squared is the same order of magnitude as that one. Order of magnitude itself is not the most important part though. It's just that I could make, if I make my epsilon small enough, I can make both of these small compared to the original c. C n squared over 2. Now let's go back here. Delete all edges between these of this particular density. So can anyone tell me a bound on how many edges that might cost? How many edges might I lose maximum? And here's where it's helpful that, it's density up to delta. Please feel free to raise your hands and I'll call over here. it's okay if your bound at first seems really dumb. Because, okay, we don't have an epsilon here anymore, we just have a delta, but we fortunately do have power to choose what the delta is. So it's okay if your bound is just like using delta to do something. Your bound actually will not have an epsilon in it. Leo.
Would we just do delta times the total number of edges between the...
Yes, let's just take delta times, how many edges could I even have? So I'll say delta m squared, that's like one particular pair of low density, times how many pairs there are, which is t choose 2. So what I just wrote here is just saying that the maximum number of edges between pairs that are not dense enough is pretend that every pair, t choose 2, every pair is not dense. And then, well, if every pair is not dense, I delete all of the edges in there. But when I delete inside, I only lose at most delta times the m squared. Does this make sense? Like, this is just using a really dumb bound. And I see, but that's why people paused. They were like, well, is this good enough? We'll find out. Let's put it together. If you multiply these, I'll use t choose 2 as at most t squared over 2. Delta m squared. Oops, that's supposed to be a t. T squared over 2. And that's equal to delta n squared. I'll write delta over 2 n squared. Now that's also good. Delta over 2 times n squared is something that I could make to be small if I wanted to, because I could go and choose to make my epsilon and my delta both small. If I accumulate all this stuff together, what I find out is that in total deletion is going to be at most, it's going to be something times n squared. So I'll put the n squared in front. Times, altogether, it looks like I have 3 halves epsilon plus delta over 2. Okay? And this thing makes me happy because I could, in theory, make these small. Remember, I'm going to choose epsilon to be really tiny. I'm going to choose delta to be the next level of big. But I could, if I wanted to, choose these so that this is all less than cn squared over 2. Okay? And that's actually what we are going to want. So we are going to choose those, and we'll make a little comment already. We'll choose those. We'll choose such that, let's call this total deletion a yellow box, such that the box, total amount we deleted, is actually less than cn squared over 2. Now there's an important thing about Tehran's theorem. At some point we have to use this 1 minus 1 over chi minus 1. Like, why is that there anyway? The reason it's there, as you may or may not remember, we actually proved that if you have at least 1 minus chi minus 1, if you have more than 1 minus 1 over chi minus 1 times n squared over 2 edges, then there's an h. Okay? So we actually have a way of showing that there's going to be an h. And if I have now deleted not enough of these edges to drop myself below the normal, sorry, not an h, a k chi minus, we'll have a k chi. That's actually what I need. So what we are using is that if I have enough edges, I get a k chi. And the threshold for the k chi to appear is this 1 minus 1 over chi minus 1 times n squared over 2. And so the important thing is because the total number of edges I deleted is giving me, it's not eating up my whole extra amount. I still have some extra. So what that means is, since still have some extra, have extra edges beyond this 1 minus 1 over chi minus 1 times n squared over 2 threshold, since I have this, that tells me that there exists a k chi. I'll say that is actually one of the punchlines. Does this make sense? This is actually very powerful. Like, somehow I got a k chi. How? It's just because I made sure that we chose this epsilon to be really tiny, so there's enough room to choose a delta, which is still tiny. And after I've done that, even after this deletion process, there's still a k chi. Are people with me here? This is actually one of the critical points of like, wow, this is amazing. Because once you have this, now we can use this for the exact result we had before. We had this proposition. Because what does a k chi look like? If there's a k chi left over, I've already deleted all the edges inside each part. So the k chi has to use chi vertices on different parts. Also, the k chi cannot use any edges between parts that are not epsilon regular. And also, it cannot use any edges between parts of densities that are too low. So this k chi happens to be chi blobs, and all of the edges between the blobs, all of the pairs between the blobs are epsilon regular, and also all of the pairs are at least delta dense. So we're in exactly the situation we were before. So what this gives you is you get a picture with chi blobs. I think I called them clusters last time. That somehow sounds a little bit more technical, but blobs is also how I think of it in my head. I get chi clusters, and they aren't V1 to V chi. They're just somewhere, these chi clusters. But importantly, all the pairs are epsilon regular and delta, at least delta, dense. Now, once I have this picture, this tells me that under certain conditions, I can actually get to have a large, complete multipartite graph. So then what we do with this is we use the previous proposition to find that there exists a k big, 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 big. How big do I want? I'm going to be very greedy. I'm going to say, let's take the number of vertices in my graph H, the number of vertices in my graph H, number of vertices in my graph H, and the number of these is going to be chi. Now, when I say proposition implies, this means that we used some conditions on delta and epsilon. And in fact, these conditions looked something like, we had some conditions, they looked something like we better have delta minus epsilon to like r times t. What's r now? R is chi. What's t now? T is this v of h. We need to have this to be true. Is this ringing a bell? Like, I'm just trying to say, here are the conditions that we would need in order to apply the proposition to go and get this piece. I would need that, the delta is big enough. I would need the other piece also, saying that somehow as I choose all of these vertices, vertices inside the blobs, I will still have enough room to choose the other vertex. And there was some other condition there. If the m was big enough, this is what we discussed at the beginning. So I'll just say there's this other condition that you put, well, we can just put it here. This was like epsilon times r minus 1 times t, as we're pulling, I need to give these the right names now. Epsilon times r is now chi minus 1. The t is now a vertices of h. We needed all of this to be like, wait a second. Yeah, that's right. We needed all of this that we eat away to be not too much, and I wrote my half, times this delta minus epsilon to the power, however many times I might compress this down, which would be like this chi times VH. Are people sort of following what I'm doing here? I want to emphasize that the exact details of like, is it going to be +1 or -1, those are all not the important part. The important part is to look at this and see what conditions this is telling you about epsilon and about the delta. And in particular, over here, we also had this thing which just Suchao pointed out, we probably should put the m in as well. But when you put everything together, why is it so interesting to be able to find this? Remember, I'm looking for an h. Why is this great if I'm looking for an h? Feel free to raise your hand. Yeah, I see some hands. I just need to scroll this to see who they are. Anthony, what do you see? Why do I get so excited with this?
Actually had a question.
A question, yes. What's your question?
So in each of the clusters,
Yes.
we have at least a number of vertices equal to the size of H, right?
Yes.
Each of those is epsilon regular, and at least delta dense to each other.
So we're getting this chi clusters.
Exactly do we have the size of H?
Why? Oh, you're asking how did we get k size of h, a number of vertices of h, number of vertices of h, number of vertices of h? Are you asking how we were able to get this? How we were able to get this is by applying the proposition with the appropriate choice of delta and epsilon, so that even after I shrink all the way down, given that that's what I'm really trying to get, I will actually still have enough space left inside each cluster, so that I can, the piece that I get at the end is still big enough that I'm able to apply the epsilon regular condition That's what this thing was. And then this other piece was, here's how many vertices we're shaving off each time. Is that making sense? So, yeah, okay. And Liam, what do you see? So why is this exciting? I saw Liam had a hand.
I'm
So.
a little bit lost still.
Oh,
on,
question. Yes, what?
How we got the chi clusters and justified that we had epsilon regularity and delta density. Are we going to justify that later, or?
Let's do that now since you asked. So we're over here, and we happen to have that. We have all of these different clusters. At first, there's T clusters. I'm glad we have this near real-time interaction. That's helpful now. So we have these T clusters. The T clusters I don't know anything about, except I know this stuff. So now, once I do all this deletion, I'm able to say that any edge which survives actually signifies something very powerful. If an edge still survives here, then that means that these two clusters have to have density, at least delta, and they also have to have epsilon regularity between the clusters. And also, any edge that survives has to be between two clusters. So I see, it's because I skipped a step, I went too fast. If I go back here, how do I know there's chi clusters? It's because there's a k chi. Going back to here, how do I know there's a k chi? I used normal Tehran theorem. Like, why this is exciting is that we're using the regularity lemma together with normal Tehran's theorem to get a normal complete graph. And then using what we just proved, we can use that to get an arbitrary graph which just happens to have the exact same chromatic number as your k chi. So once we get this k chi, this part comes from the Tehran result. And once we have Tehran for like normal complete graphs, why are there chi clusters? It's because actually you're able to find a k chi. There's a k chi, and the k chi happens to have all of its vertices in different clusters. Did that make sense now?
Yeah, that makes a lot of sense.
Yes, and thank you very much for raising that. I see more hands. So Ariel, you also have a question or an answer?
Yeah, so if you have a K with the vertices H and chi of them, then you can, like if you have a coloring of H with chi colors, then you have each cluster is a color.
Great. So I hear this. You were basically answering the question of why this is exciting. And now I see why we will be very good as soon as I can get a headset on this side so we don't have the feedback going back and forth. But over here, it's like, why is this exciting? The reason this is exciting is because this actually contains H as a subgraph. And the reason it contains H as a subgraph is because you could take any favorite coloring of H you want. This actually, when I first learned it, took me a while to appreciate, so I'm going to just emphasize it here. Why is that true? It's because you can color H with the chi colors. And so when you color H with chi colors, we would say, here are some vertices of H, which are the color 1 vertices of H. Here are some vertices of H, which are the color 2 vertices of H. And here are the color chi vertices of H. And H itself is some graph. It's not a complete multipartite graph, but it's some graph that goes between all of these, right? It's like there is some graph, and the way H would look is that H has no edge, which is entirely inside one of the clusters. What that means is that H is part of some kind of a k-partite, multipartite graph, but certainly the size of each part is less than number of vertices of H. You can't have more than that because you only have VH vertices at all. So bam, you got the H. So then when we put everything together, I mean, in this last one, again, I was kind of lazy with this 1/2. Really, you also need that the M is big enough. Okay, and the M multiplied by this needs to be big enough. And so when you put everything together, what you find out is if you just happen to pick oh yeah, just a second. So how do I know the M is big enough? That's actually also important. You know what? Let's actually put it here. So now I see it's much better to just write the whole thing down for the second line. Let's do that. The second line is, what might I have shrunk to? I might have shrunk to delta minus epsilon chi VH as I'm doing my shrink and getting these tiny little neighborhoods in the parts. But then in the last bits, I have to also take away these epsilon fractions. And maybe I do it r minus 1 times, I'll call the r is chi. Let's just call it chi, that's good enough. Times, take away r minus 1 times, right? And these are times m. You take away epsilon fraction and you take it away that many times. And wait a second, I'm trying to think of which way we want it. No, it's not, I flipped the r and the t. This particular one is t minus 1 times. So this one we would want vh. But again, this is not essential because this is just showing where you're losing. So t minus 1 times. So if I take it away that many times, I need that this somehow still has enough vertices. So enough vertices to pick the last one. Are people with me on this? So this was basically saying I took this tiny, tiny little neighborhood that was left, the common neighborhood, and then as I did my deleting and deleting to make sure I could still be with the right degrees to the remaining stuff, every time I delete epsilon fraction of the m, and I do this at most this chi number of times because I from here, wait a second. Is that right? No. I delete this actually at most, it is chi times. Or does somebody remember? Actually, this way I can also make sure people are with me, right? So how many times do I delete? It's actually for each one. I need to delete once, possibly for every other person, right? So that's actually not going to be a question of the VH. That's going to be a question of the chi. I'll go back to the chi. Okay, are people okay with this? It's like because for each one, I will take away some amount corresponding to bad degrees into each of the other ones. And so when I have this, I need to have this be at least 1. And that's where you can see that the m starts to play. How do I force the m to be big enough? Well, to get this particular line, the value is that I have a lower bound on m. M is equal to how much? Well, m is equal to n over t, which is at least, here is finally where the capital M comes in the similarity regularity lemma. That's actually why I want to do this in full detail. You see, because the little t is at most capital M. So I can write n over capital M. Okay? So then that's good, because if I have n over capital M, if we look at this expression that's here, most of the stuff are constants. Chi is a constant. H was given. This v of h is a constant. That was given. This just tells me over here, these two conditions, I can make these two conditions happen by choosing delta and epsilon to have some dependency, which is just like, delta is small, and then epsilon is even smaller. Does that make sense? I can satisfy these conditions, all of these conditions, can satisfy all by choosing this epsilon much smaller than a delta, and you can much smaller than 1, and you could do it even in a very definite way. You could actually write down an explicit formula for delta in terms of epsilon, or epsilon in terms of delta, whichever you pick, which just uses these exponents. And this you can do explicitly if you want. Okay, once you have that, then this whole chunk over here is just some constant. So in order to get this to be true, I would then just need n, my little n, to be at least my capital M times whatever we need to overcome for this constant, right? So when you put all of this together, after you have chosen this, the m, by the way, came out of the epsilon. I want to show that all of these choices are consistent. I'm writing this whole thing down first, then we'll chase the choices, right? The m, by the way, is itself dependent on epsilon. Maybe I'll emphasize it here by saying m of epsilon. That's not m times epsilon, that's m of epsilon, depends on epsilon. And so when you put everything together, you can satisfy all of these bounds if your little n is bigger than some monstrosity. So it's true if your n, little n, is bigger than some enormous number. It will have your m, depending on epsilon, times whatever extra stuff that you get as a consequence of this piece, right? So that's huge, by the way, but that thing is what you'd call capital N. And so now I know it's actually over time for this class, but I just want to show how everything traces together. The way everything traces together is, I need to show that given the C, I have a pathway to define my epsilon, define my delta, define my capital M, and so on. So from the before, we saw that with some conditions, we need to have that, this particular thing here. I'm going to delete this this many edges. I need that to not cost me more than my c n squared over 2. That gives me a control on how big epsilon and delta can be. And so I'm going to pick delta to be small enough and epsilon to be even smaller so that I delete not so much and I eventually get my k chi. Once I get my k chi, I'm able to go into the next page and say, since I have my k chi, oh, by the way, my epsilon delta dependence needed to have been chosen according to the function that comes from here. So since I was able to do that, I'm able to just say that this last piece is true because my number of vertices is big enough, because I defined my n this way. So chain is C gives you, this thing gives you the delta epsilon dependence. C tells you really how small to pick that epsilon and delta. Once you've gotten the C giving you something that small, then you can go into here, figure out what m spits out, because m is a function of epsilon. And whatever m spits out, you find this lower bound capital N, which is huge. But this proves Erdős-Stone-Simonovitz. We are over time, but are there any questions? So at this point, the class is officially over. We could pretend that we all walked out of Wien 8220. But if anyone wanted to stay afterwards and ask any questions about what we just saw, feel free to raise your hand. I hope that this is, I want this to be fully understandable because this is a beautiful proof. Actually, if you get it and just if it's good, we are also okay with that. So it looks like I don't see any questions. So in that case, I'll say thanks for everyone. We'll see you guys on Monday. And what I'll say is that I'll say goodbye to the people who are on YouTube. That one I'll stop. If anyone in the class wanted to discuss anything else about the way that this class ran, I will continue and do that now. So I'm going to stop. I'm going to stop streaming this onto YouTube. And instead, I'm going to switch into the Zoom call and directly interact with whoever's left in the classroom about feedback on how this particular online class went today. So rest of you on YouTube, see you later.